and welcome to my lab. I'm especially pleased that you are here to celebrate this very wonderful anniversary. And I want to thank the UW band for being here. Weren't they great? They'll be back. They'll be back. So thank you very much. Appreciate your being here, and we'll see you shortly. So I ask you to pay attention, because if you pay attention, you're going to learn. And I want to make sure that you are really paying attention. What does my T-shirt say? Oh, come on. You can do better than that. What does my T-shirt say? That's it. We need to have some enthusiasm as we do experiments. I'm going to use these 4 beakers that have in them the same green colored liquid, and I'm going to add different clear and colorless liquids to them, and we'll see what happens. So I'll use this one on my right, on your left as a reference. I open this container and I add some household ammonia. You like that, huh? I'm glad you like that. I like that too. Color changes tell us that something is happening, and in science we try to understand what it is that's happening. So I take a different clear and colorless liquid now. I add that, and you get another transformation. Here's a third clear and colorless liquid. What would you predict is going to happen now? Any color change? How do we find out? Just stop talking and do the experiment, right? Here we go. And we can mix those. And we can mix this one too. You notice this one has a solid at the bottom. Let's try to mix it, see if the solid disappears. And we get these beautiful color transformations by adding different liquids that combine with the heavy metal that's in there. The green color is because we have something called nickel sulfate. These are compounds of nickel that are combined differently with the different reagents that we have. So here's another one that I want to do. I have a beaker. It's empty except for air. It's the same size as the other beakers. You're paying attention, right? Because if you pay attention, this is how you learn. And this is how we process information. And this is how we start sharing information as we learn from what we have observed and make connections with the experiences that we've had. So this beaker is empty except for air. I'm going to take a clear and colorless liquid and put it in it like so. And then I'm going to put the cap on. Why do I put the cap on? Just in case I knock it down, right? We practice safety all the time. And then I take a clear and colorless liquid and add just a little bit of it, and there we go. And you like this one? Now I want to walk over and do an experiment right here, where you see I have a large flask. It's empty. Actually, it's not empty. It has in it a clear and colorless gas. And it is connected to this large beaker that has water in it. And there is a stopcock here, which I'm going to turn, and then I'm going to also squeeze the small rubber bulb that has in it just a tiny bit of water. So first, I open this, and then I squeeze. And a small amount of water is dissolving the gas that's up there. The gas is called ammonia. Ammonia is very soluble in water. And then the pressure in the upper flask gets to be lower than it is, and you see the atmospheric pressure is pushing, siphoning the liquid up here. The next experiment I'm going to do has to do with water. And I have several beakers. 5 of them are the same size, and this one is bigger. And then I have 2 of the beakers that have water in them. And what I'm going to do is use some household chemicals to study some of the properties of water. The device I'm going to use is this light bulb that is not lit right now because the circuit is not completed. It's plugged in. But let me show you what happens when there is conductivity. You get a bright light. So if I take this apparatus and I put it in water, I don't see any light coming on at all. That's because water is a poor conductor of electricity. If I go to a different liquid, which I'm going to add right now, this is household chemical, ammonia. I'm sorry, this is vinegar. And then this one is the ammonia. Well, let's see if we can learn something about the conductivity of vinegar. You can't see the light. Can we turn the lights down, please, just a little bit? So vinegar is not as poor a conductor of electricity as water is, but it is very, very poor. So I take this out with the lights back up again, please. And I rinse in here in between experiments because I do not want to contaminate the vinegar with the household ammonia. We try the ammonia. Let's see. Can we have the lights down, please? It is also a weak conductor of the electric current. That means that ammonia, household ammonia, and vinegar do not have many ions in them. So I rinse one more time. And then I'm going to go back to the ammonia. Now I want to add, with the lights up, please. Now I want to add the vinegar solution. With the lights up, please. Thank you. And as I add this, you see me do it. Whoa is right. When you mix the ammonia with the acetic acid, you get ammonium acetate, which is a very strongly ionic substance. And so we learned from this experiment that the electric conductivity is a way by which we can tell how many ions we have in solution using this very simple device. And by the way, this is an experiment that you can do at home if you have a device like this. And if you go to my website, scifun.org, you will find the instructions for making a device similar to this, so you can do this experiment and many other experiments that have to do with conductivity. Please welcome to my lab the Pro Arte Quartet. Thank you, colleagues from the School of Music. Thank you. Ladies and gentlemen, one more round of applause for the Pro Arte Quartet. At this time, I would like you to welcome someone who's been working in my lab. Please welcome Julia. Hi, Julia.
Hi, Bassam.
Happy to see you.
Good to see you, too. How are you?
I'm fine. What have you been working on?
Well, I've been doing some experiments with air movement. Air is a fluid and it moves, but everybody knows that, right?
Yes, yes.
So I have here a balloon.
Yes.
And I'm going to blow air, that is, move air into it, and it will inflate. So you saw that I had to blow harder when I inflated the balloon initially.
Yes.
And then once I stretched the rubber out, it was easier. But you've inflated balloons before, right?
Yes.
You guys remember that, right? Oh, no. This one has a hole in it.
It has a hole in it. Oh.
We'd better get another one.
Well, we have more balloons.
Okay, we have more balloons.
Yeah.
A little too big, I think.
That's good. So air movement, you blew air into the balloon, you inflated the balloon.
Yes.
You worked harder at the beginning. Everyone knows that.
All right.
You tie the balloon.
You tie the balloon. This one doesn't have a hole in it. Good.
Good.
Now, I also have here a hairdryer.
Yes.
And when I turn the hairdryer on, a fast stream of moving air is going to come out of the nozzle. Now, if I take the balloon and do this.
Whoa.
Yeah.
That's cool.
It's suspended in the moving air coming out of the hairdryer.
So the stream of air that's moving from the nozzle is holding the balloon up there?
Right. So if I block the air, the balloon comes down. Pretty cool, huh?
Yeah, that is cool.
Now, watch this. Whoop.
Whoa. Bravo, Julia.
Thank you.
That was really cool.
Thank you. Now, air movement is what I want to tell you more about. So I have another experiment that I want to do, and I want you to help me with it.
You want me to help you?
I do. So
I'm ready.
Here, let's take this, and let's move around to the front of the table so everyone can see. Okay, so I have a long piece of plastic here, and I'm going to give you one end.
I can see that.
I'm going to hold the other end.
Yes.
There's an opening at my end. Is there an opening at yours?
No, mine is sealed.
Okay, here. You take this end, and I want you to inflate this long tube by blowing into it. Yes.
This whole long tube?
Yes.
Just blow air into it?
Yes, and we're going to count how many breaths it takes for him to inflate it, okay?
Okay.
All right. 1, 2, 3, 4. Oh, okay, you can stop. I don't want you to hyperventilate.
Yes,
now,
thank you.
Let's see how well you did. All right, not too bad, not too bad.
I tried.
Yes. Okay. Now I want to show you and everyone else how I can inflate this with a single breath.
No way.
Watch. Here, you take this end.
This is the sealed end.
That's the sealed end. I'm going to take the open end. All right. Now watch this.
Whoa.
So
I like that.
what happened is when I blew a stream of air down the middle of the tube, it created a partial vacuum around that stream of air, and that sucked in more air from around it.
Uh-huh.
Would you like to try it?
Sure, I'd like to try it.
All right, let's...
Where are you from, Julia?
I am from North Carolina. I was actually homeschooled in North Carolina.
Oh, really?
Yeah. I went to college when I was 11 years old. And I graduated from the University of North Carolina, Wilmington, when I was 16, with bachelor's degrees in chemistry and biology. And then I came here to the University of Wisconsin-Madison to enroll in a biophysics graduate program, and I got my PhD in 2017 when I was 23 years old.
Whoa!
But I want you to try the experiment
yes,
this fall.
Dr. Nepper, I will do whatever you want me to do here. So let's see, I hold this up like this, right?
That's right.
And then what do I do?
Just blow a stream of air down the middle. Okay, now close it off quick. Wow! Great job, Bassam.
Thank you so much.
I love working in your lab.
I love having you in my lab too. Thank you so much. Please give a big round of applause to Dr. Julia Nepper. My next experiment is going to be done using a very cold liquid. This liquid is called liquid nitrogen. Liquid nitrogen is kept in a container like this so it remains cold. And I have two other small containers that I'm going to retrieve and use to show you some of the properties of liquid nitrogen. So I take the liquid, now it's heavy, I put it in this thermos bottle that's clear, and you can see the liquid boiling. That's because the glass is at a higher temperature than the boiling point of liquid nitrogen. Liquid nitrogen boils at minus 196 degrees Celsius, really, really cold. And it continues to boil until the temperature of the glass gets to be the same as the temperature of the liquid. So we're losing a lot of heat here to liquid nitrogen. You fill it up. And one of the interesting properties of this liquid is that you can pour it on, use it for dusting, just like that. It's a very expensive way to dust things. So there are lots of interesting things that we can do. Here is a balloon tethered, as you see it. I'm going to pull it down, and I'm going to pour some liquid nitrogen. Oh, some of you are covering your ears again. So I add this. And what's happening? The balloon is collapsing because the helium atoms that are inside are slowing down because of the cold temperature on the outside. I pour the liquid out. It's all gone. And now as the liquid evaporates, what happens to the balloon? Goes up again. I need a little more liquid nitrogen here. You can see when the cold nitrogen gas comes out, we get that condensation again of the water vapor. And what I'm going to do next is take one of these chrysanthemums. It's a nice piece of flower here, right? And put it in the cold liquid nitrogen. And I'm going to pull it out. It's not as pretty as it was before, and it's much more fragile than it was before. You have been a great audience, and I want to thank you for coming here to share in the joy of science, enjoy the arts, and to be enjoying whatever else you do when you do experiments. Thank you very much for coming to this special celebration. I want to invite all my co-workers to come out. Come on.